and joined PRL, where he's presently an associate, and he's one of India's leading experimentists in optics, I must say. He's working on all kinds of very, very interesting things, which is like quantum optics, which involves like entangled photon sources and sensing, quantum sensing, as well as, the classical optics, classical optics, nonlinear optics, and things like structured beams, parametric oscillators. Very, very diverse range of research on optics. And he's also a very, very good speaker around there. I think the students will have a very good time now with Goutam, giving his talk. And so I think, Goutam, have you shared your screen?
I see it. Is it visible?
Yeah, of course, yes, it is there. So this basically is talking today on entangled photons, which is, of course, very much commensurate with the QIQT theme. And let us get enriched by Goutam's experiences in generating this. Goutam, with you.
Okay, thank you very much. And it was really a nice, it sets the introduction itself sets the environment or the mode for this presentation. So today, as already introduced, I am Goutam Samanta. I'm a faculty member in Physical Research Laboratory. And today I'll be just talking about the entangled photon source that can be used for satellite-based quantum communication, what India is planning in future. Okay, so before going, I take the privilege to introduce something about the group and the laboratory where we do work. That is basically the front gate of my laboratory. And in case you are interested, you are always welcome to visit through different ways. You can directly visit PRL, or there is a student conference organized every year that is called SCOPE. Mostly it's in September, so you are welcome to that also to visit us. So then when you have a lab, then you should have also a bunch of very energetic people, those who will be performing some of your ideas or work. So that's why I have a group of people. Those most of the cases will be working and playing in the ground. So you can just see the leftmost corner photograph. They're playing football because we play with photons. So outside we play with football. And when they are a bit sober, come with this kind of dress in the right side, come to the lab and do some of the interesting work that I'm just going to present. And I'm also happy to have a good collaboration with my former group and then my friend in IIT Bangalore and some of these from Mexico and Hong Kong and a professor Andrew Forbes from South Africa. As Andrew was saying, we do work in various topics, including this nonlinear optics and classical, mostly the classical optics based on this nonlinear interaction. Then studying the structure optical beams, how they interact with the nonlinear medium. Then means once you are just dealing with nonlinear optics and then laser light, so you can just create entangled photons. So that is what we also work on that, and some of the other projects that in pipeline. Okay, so to just give the brief outline about the topic what we work in the field of quantum optics in PRL or especially my group, it will be something like this. It is a very recent demonstration I have just put. One of them is a free space QIQT over 200 meter in PRL that we have developed the source here and then demonstrate over the, so over using two building terrace, you can just see here, then we have just demonstrated that. This communication also repeated over free space in collaboration with SAC. That has come in news, you have seen, and Chairman ISRO has also announced the successful demonstration of this 300 meter free space channel, QIQT, and then having that video conference in SAC, Ahmedabad. We also work with a single photon and studying its interaction, so like if you're just having an interference of single photon, how the photons can interfere if you are just having a single photon. So basically, Sasi today morning, you are just explaining about the vortex beam, or if you have a beam which is having orbital angular momentum, that you can transfer the classical orbital angular momentum of the classical beam that can be transferred to the single photon. So that is what we have just shown. These images are basically the images, coincidence images of the vortex of the single photons, and depending upon the orbital angular momentum of the input pump, we can measure the orbital angular momentum of the single photon. We also made this. We are also working on that, how to make a space or the entangled photon source that I'll be explaining today, so that in space condition, when you are just working in the lab, you are having all the resources, and then you have that luxury to explore many things, and then environment is very stable. But when you're just sending something to space where the constraints are huge, and then you don't have much control over the system, then you have to make the system it's a robust itself, so that it take care of any change happen, it take care of it by itself. So that is what we are just trying to make. We also make the prototype system. Basically, this entangled photon source, we just make a prototype system that is being now made in the lab. So it will come in a box of 20 centimeter by 20 centimeter, in that kind of area we are just making, which will be a bright entangled photon source that can be used by anyone in the field, because it's required only a one input and the rest of the things are there inside. So you are just plug in, and it's a plug and play kind of device we are just trying to make. Then we study also Hongo-Mendel interference of the pair photon. So when you are just having these photons, you can see this due to this bosonic nature. Philip was also explaining. So they will be following a delay. So it's a bunching will be there. So when these photons are completely indistinguishable in time and almost all degree of freedom, so then there will be zero coincidence. So, and then if you just keep on changing that delay or the distinguishability, if you just keep on adding, then they will be having some coherent this coincidence. So as you can see, this is a line over which you can just use. So if you just project that in the x-axis the delay, so you can just have a amplification, because this line is something a linear kind of thing, where you can just it's just simply like the amplifier system, where you can have a small delay variation or fluctuation, anything that will be amplified and you can sense. So that is what we are just using this HOM interferometry to study for the quantum sensing. So for small, let's say, refractive index change or anything that we are just, or polarization, rotation, those are the things we are just working. This is the photograph of the payload what we have just built. It's being made by our technical support team from SAC, those who are just making this system, starting with the architecture what we have just provided. Anyway, so why quantum entanglement? So it's already, because there are so many sessions people have already explained, so I'll not be going to the details, but that the major attraction to this field and then major investment to this field I see came from this report, where China successfully sending the payload to the space and then demonstrating QIQT over 1,200 kilometers apart in the space position in two different distinct places, which is a separation of about more than 1,000 kilometers or so. So this is basically just a starting point for many of the people just coming in and then taking the advantage of it, and then trying to explore the possibility of putting or pushing this technology further and making each of their countries just as self-sustainable in terms of this quantum communication. And India is not lacking, so we all are also working towards that to put India making quantum enabled. So on top of that, this one entanglement can be used for various other things like quantum teleportation and quantum cryptography, where you can just have do the performance on this quantum security thing, and then you can just have that super dense coding. And if you just say why and what is a quantum entanglement, basically it's a for long distance communication, let's say free space communication, one need to what are the limitations? Basically, if you're just trying to do a long distance communication, then what are the things you need? So in any long distance communication, the loss in the channel itself is something that cannot really just avoid or overcome. For that, to overcome such situations, one has to improve the source itself so that you can just have a long distance communication. That's why we are just trying to address, let's say, increase the large number of entangled or improve the brightness of the entangled photon source. And at the same time, for secure and high information capacity communication demands high dimensional entanglement. So where you need to really create the entangled state in higher dimension. So these are the two things what we are just addressing in PRL, and there we are implementing also for quantum communication. So mostly I'll just talk about the high brightness and then high dimensional entangled state, perhaps just some other day. So entanglement, you have already heard, so I'll not go into the details. So just to put the things in a right perspective, basically two photon measurement of one can be, because in case you don't quantum states of two or more objects that has to be described with reference to each other, or even though the individual objects may be spatially separated. In that case, the measurement in one will reveal the parameters of the others. So that is the interesting property of this entangled state. And how we realize that is very important. So we in optics, so what we say that quantum entanglement or the state preparation, in optics or typically this parametric down conversion process is used, where a pump photon goes to the nonlinear crystal, generates into two photons. That is what is called signal at that. And most of the cases, your pump photon will do nothing. It will go or transmit to the crystal. But once in a while, it will just translate into two photons. And these two photons basically satisfy the conservation laws. One is the energy conservation, another one is the momentum conservation. So energy is basically the energy of these two photons has to be equal to the energy of the pump photon, because it's a parametric process where the system parameters remains unchanged before and after the operation. But since we are saying that these two photons are having two different wavelengths it can have, and the material dispersion comes in, so the momentum of the photons will be very different, because three photons are having three different wavelengths, then their momentum will be there, and there will be a momentum mismatch among them, for which the energy transfer from the pump to the generated photons will always be limited. So one has to really just make the momentum matching so that you can transfer the pump photon or energy of the pump photons to the generated photons. So that is what one can use. There are various techniques. These are the three typically used techniques. One is type 1, type 2, type 0. So in type 1, basically the pump photon will be having the orthogonal polarization. The generated photons will have the orthogonal polarization to the pump, but the pump generated photons will have the same polarization states. Like we are studying with ordinary polarized photon in the pump, they will having orthogonal polarized, but they are same polarization for the signal and idler. In case of type 2, these generated photons will be orthogonal, but in case of type 0, basically all the photons will have the same polarization state. So the advantage is when you are just trying to use two different polarization states, then the material refractive index is also a polarization dependent parameter. So due to the change in the polarization and wavelength, the refractive index will be different. But here, so that's why typically this type 1 and type 2, we have this special walk-off effect, which we typically see, because when you are just having this kind of photon, so due to this special walk-off, due to this polarization difference between these photons, they always try to walk off from each other. That is why where limits the length of the nonlinear interaction or length of the crystal. But in case of type 0, even though you have two different wavelength, but since the polarization states are the same, so you can use a longer crystal or longer nonlinear interaction path one can have. So as a result, one can basically generate more number of photons using type 0 process than type 1 and type 2. But unfortunately, in case of type 1 and type 2, that is what is the initial stages. So I'll just come to that one, what we are just using to enhance the brightness of the entangled photon. So typically you can just have this kind of SPDC photons or down converted photons that is coming in a special distribution. Because here, if you have, you can see a signal idler, and then I have to separate them. But these two photons will have the same polarization, and they can also have same wavelength, because you have just, if you're running in a degenerate state, then they will have the same wavelength. So it's very difficult to separate them individually from the superposition, because if it is a collinear, then it's very difficult to, you cannot really just do that one. So for that, people try to go to the non-collinear geometry, where these photons will be distributed over a special ring or annular ring, and the pair photons will be always diametrically opposite points. In case of type 2, since these two photons are having different polarization states, so you can use anything like polarizing medium to differentiate the photons. And type 0 also, there is another problem, same problem, because if the photons are since they are having the same polarization state, and like type 1, is the same problem will be there. So one has to really just use a novel technique or architecture to translate the collinear geometry or the collinear superposition of these generated photons in a non-collinear geometry that we have just, I'll go in details while I just going in the following slides. Okay, so these are the process, and just to understand then how do we really just see the entanglement or not. So for that, this is the cartoon I am just showing. Let's say if you have a BBO crystal, nonlinear crystal, where pump is passing to the nonlinear crystal, and it's creating a type 2 process where the generated photons are orthogonal in polarization states. Let's say the vertical is a orthogonal, vertically polarized light is depicted by the green, and the photons are basically just distributed over the ring. And horizontal polarization is the ordinary polarization that is basically defined or identified by this red curve. And due to the as I said, that momentum matching or energy conservation, so if I find a photon from here, I can always find a photon on the other side, basically due to this momentum matching or the conservation. But the interesting point is, so if you just collect photon from this intersection point, and we don't know whether that is coming from the red or the green, so it can come from any one of them. At the same time, in the superposition position, where you can have the photons either coming from here or the red line, red circle. So that means if you are just trying to write the polarization, the state between these two points, then we have to write basically the superposition of this plus this photon. So basically that is what give you the sense of entanglement. And if you measure a photon that is coming from the green, then this photon has to be always, it will be always on the red line. So basically that is what we say entanglement. And if you in the lab, even though I have just shown in the cartoon, but in the lab you will be seeing exactly this ring what I said. This is the image recorded here for type 2 SPDC in using a EMCC camera. So so basically these things I'm just explaining some basic, because there are many students, those might be new, and many are experts. So this section is not for the experts. So once you have these photons generated, then you have to really verify whether you are generating the entangled photon or not. So this cartoon basically shows how you just make the measurement. So basically, if you have this pair photon, they are just going into the two different parts of the experiment, and then you have two analyzers and then for detectors, and then we are just measuring the coincidence. If the two photons come in a particular time interval, then we consider the coincidence. So that is what we measure the coincidence. Now, if you make the keep the analyzer fixed at a particular condition, or let's say polarization state, and then if you keep on changing the polarization state of this photon, then we will see the variation in the counts. So that is what we do. And then once you have this kind of interference, then we measure the Bell's parameter and then find whether the Bell's parameter is more than 2 and the maximum 2√2. And then we also study the density matrix of the state to establish what state we are just creating, and then what is the state fidelity. And one can also do the speed number quantification for these biphoton modes. Anyway, so if I'm just, as I said, that how the interference look like. So here, basically, we are just, these are the 2 points we have defined by these 2 lines, and the photons are collected by this one detector, another detector here, and keeping the polarization state here. So let's say P1 polarization fixed, we kept the fixed, and then P2 we keep on in changing then you will see that in coincidence, the number of coincidence will go down because you are just rejecting the partner photon. That's why the coincidence will go down. But here you can see the count remains unchanged. So this is the important parameter you have to maintain. So even though you are just changing this polarization and rejecting many of the photons, but that count has to be constant. Otherwise, you can just get this kind of pattern if your because if your photons are not coming, in any case you will see. So that my overall count should go also down. But since it's not going, that means this is only the coincidence going. That gives the sense of entanglement. And then the visibility of this curve will be a direct estimation of the entanglement. So for this example, let's say we have just measured the visibility is 91%. And then if the visibility is more than 71%, then you can ensure that it's just entangled. But the Bell's parameter will be close to 2. So for any communication or for any effective use of this kind of states, you should have a very high Bell's parameter, so that any perturbation can still lead you to the entanglement. Otherwise, it might just destroy. Okay, so photons entanglement can be, these are the things. Basically, it's a different degree of freedom, polarization, and polarization. Basically, I was just explaining so far is the polarization basis, where you have two polarizations. It can be two bases, but orbital angular momentum you can just use, that can give you infinite basis. So you can just have more information capacity. And typically this, as I said, that one of the important source for this entanglement is a spontaneous parametric down conversion. Okay, so I'll not go to this one. So for long distance communication, if you are just trying to have, then you have to improve the brightness of the entangled photon source. Then you have to improve the efficient transmission channels. And then photo detection is also another direction where one has to work to. And all these three things should come together to make the feasibility of long distance communication. So I'll be just talking about the brightness of the entangled source. So as I said previously, people normally use the existing techniques for generating entangled photon source is a birefringent medium, basically type 1 or type 2 phase matching. Waveguides are also used, but it has its own limitations. And then bulk crystals are used. So few drawbacks is basically just number of photons, and then this nonlinear coefficient. Basically, the nonlinear coefficient of the materials, basically Chi2 coefficient is very small. So you have to find out material whose Chi2 coefficient is very large, or you can just improve the coefficient even the coefficient is low. If you can just use a longer crystal length, then that nonlinear gain will go up. So just to put those things, summarize the things in one slide, I'll just put that one like this. So parametric gain is very low, so we have to improve the parametric gain. So by increasing the length of the nonlinear crystal, and if you're just increasing the nonlinear crystal, then the special walk-up comes in, because you are just using two different polarization state for the signal and idler. So the special polarization, special walk-up, if you want to remove the special walk-up, then you have to go to the periodically poled crystal, where type 0 phase matching is coming into picture. So once you go to that periodically poled crystal, then type 0 phase matching, where both the polarization, both the photons are having the same polarization state, then that is a problem. That's why people use periodically poled crystals for type 2 phase matching. But then again, all the problems that I have explained so far will come into that one, even though you are just using a periodical poled crystal, but the effective nonlinearity or highest nonlinearity is not explored in that case, and special walk-up itself is there, so that will also limit. So in any case, to enhance the conversion efficiency or the brightness of the source, one has to use this periodically poled crystal for type 0 phase matching and degenerate phase matching. So you have to use a type 0 phase matching, then only you can go get that highest nonlinear coefficient of this periodically poled crystal, and then it has to be degenerate, because if you can just go away from the degeneracy, then the nonlinear coefficient goes down, or nonlinear gain goes down. So you have to, if you want to access the highest gain of a periodical poled crystal, these are the two conditions you have to satisfy. One is the degenerate process, and then type 0 nonlinear interaction. So when you are just trying to address these two, then problems comes, because the degenerate photons will have uh, have same wavelength, and type 0 is same polarization. So these are the two problems typically used to separate the photons, either by a dichroic mirror or a polarizer, means polarizing beam splitter. But none of them will work in this geometry, because a degenerate is the same wavelength and type 0 is the same polarization. So then you have to really devise something that will give avoid those problems. So that is what basically in a non-collinear geometry, where type 0 phase matching. So in case of non-collinear geometry, what I am just saying, let's say if you have a periodical pole crystal and then pumping with a pump beam, and then trying to measure the SPDC photons. So when the this is the basically a degenerate wavelength, where you will see the spatial distribution of the generated photon is Gaussian. That means I cannot differentiate whether the signal idler, where are they. But we found that when we reduce the phase matching temperature, means reduce the temperature of the crystal away from its degenerate temperature, degenerate collinear temperature, then this Gaussian distribution or the collinear geometry turns into non-collinear geometry. That means the Gaussian distribution initially will turn into the annular ring, and that the size of the annular ring depends upon the phase matching condition when we are just varying. So you can control the ring size depending by simply adjusting the phase matching temperature of the crystal. And in this case, so these photons basically will fall, or the pair photon will lie on the diametrically two opposite points. So if you are seeing a photon from one side, then its partner will be always on the other side. That is what we want. So the non-collinear geometry, so that means it's a what I was just explaining so far. So to access the highest nonlinear coefficient or highest gain in case of nonlinear interaction or single photon generation or SPDC process, we have to use a longer crystal or higher gain or highest D effective. So, but the limitation was there, because the technical limitation to separate the photons, but we found something where we can see these photons will be distributed. That means we are getting all the benefits and then getting, but at the same time we are just separating the photons. So it keeps basically the access to produce high brightness entangled photon source. So just to explain this geometry, how we are just translating from the collinear geometry to the non-collinear. So you can just see the pump photon goes here, and then generated photon will be diametrically opposite. And then when it keep on changing the temperature, so then refractive index, because this material's refractive index is a function of temperature. And then when you are just changing the temperature, then the refractive index will be changing, will vary, and then refractive index variation gives the phase matching condition different. And gradually, if you can just do that one, that is what we end up. So from collinear to non-collinear, you can just translate by simply changing the nonlinear crystal temperature. And if we measure the let's say normalized intensity of these photons, in case of degeneration, you can just see when it's a degenerate, this is the gain. When it is non-degenerate, you can see the gain is half. So that means we have to operate that just to establish the point what I said. This is the experimental confirmation where we can access the highest gain when we are using it at the degenerate condition, where the signal and idler will be at the same wavelength. So once we have this, the source, and then you have devised a mechanism to separate the photons, then let's try to use it for an entangled photon source. That is what we have just used. So we have used a sanguine interferometer where nonlinear crystal PPKTP is sitting here. And the pump beam, which is a diagonally polarized beam, pass through the nonlinear, pass through this lens. Its lens is used to focus the beam at the center of the crystal. So the pump beam, since it's a diagonally polarized, and then we have a polarizing beam splitter cube, which will reflect the vertical polarized pump and then transmit this horizontally polarized pump. So now take one. So this vertically polarized or the clockwise direction pump beam will go through the nonlinear crystal, generates its pair, as I explained previously. So it will create that pair photon like this. And then once it's going, this, because the generated photons will be also vertical polarization, depending, since we are just using type 0 phase matching. So the vertically polarized photon will be converted into a horizontal polarized photon due to this lambda/2 plate, which works for both the pump and the generated photons. So it will transform the vertical polarized photon into horizontally polarized photon, and when it comes, and this is also a dual wavelength. It's work from both the wavelengths, so it will transmit. So that means one direction it is this. In the other direction, if it is a horizontally polarized photon pump, and due to this lambda/2 plate, it will be converted into a vertically polarized pump, which will go through the nonlinear crystal, generate its pair, and that pair will come, and it's a vertically polarized, so it will get reflected. So now we can have the superposition of clockwise photons generated in the clockwise direction and the photons generated in the anti-clockwise direction or counterclockwise direction. So now these two, this is basically, if you just put a camera here, we'll see a SPDC ring. And then what we do, we just separate this ring. We divide the ring into two parts to identify the diametrically opposite points, and that we collect using the fiber and then analyze it, as I explained, using this analyzer in both arms, and doing the measurement, coincidence measurement. So when we are just doing this, let's say in the clockwise direction, we'll be seeing the photons generated in the clockwise direction, it will form in a SPDC ring like this. And then the photons generated in the counterclockwise direction will be the same, like this vertical, and then distribution. And then if we just adjust their overlap by tilting the mirrors, then you will see, you can just have this where it will be basically, overlap, perfectly overlap, where you cannot distinguish the photons, whether it's coming from the clockwise direction or anti-clockwise direction. Now we collect the photons from these two rings, what I have marked with the circle. So from those two parts, because it's a diametrically opposite, and then we get the partner photons. Then what we do, basically, since I'm just talking about the enhancing the brightness, then you have to explore all possible parameters to enhance the brightness. So once we have just used the nonlinear crystal, those are the things. So once it's fixed, then we have to just use a different pump beam, so that pump beam intensity also, where nonlinear interactions are intensity dependent phenomenon. So if you can just improve the pump beam intensity, then you can improve the generation rate or the spectral brightness. So here we just use a different pump beam waist or focus beam and measure the spectral brightness using a single mode and multi-mode and single mode fiber. And then we found there is this optimum beam waist condition required for this kind of process to give the highest brightness. So in both the cases, we can just get something around 50 to 60 micron in that range, which gives us the highest. So that is what we select. Okay, and then we also studied that, let's say we just increase the pump power, whether the linearity is there or not. Means if we keep on just increasing this pump power, and then the conversion efficiency or the brightness has to linearly go up. So we just change the pump power while collecting using two different fibers. One is multi-mode and another single mode. In that case, you can see that the spectral brightness is increasing. And this is basically the fiber coupling efficiency, where this parameter is basically how many coincidence to the total singles count. So that is the ratio. So we can see that out of 100 photons detected by the fiber, the 20% of the photons is giving a coincidence. So that's a good number, but one can improve. If you can improve through some collection device, then this number will give even it can go even more, and where the spectral brightness of the system will be even more. Okay, but that collection system doesn't depend upon the generation process. That's why we don't want to really just confuse with that one, whether the brightness will be more of the source through this collection system or not. But the generation rate remains unchanged. And if you are just collecting it, then your process looks, you have more photons to manipulate in other experiments. And then we did this coincidence measurement for single mode and multimode. And as expected, the single mode multimode is having a lower visibility, and then Bell's parameter is poor, because as you can see, this SPDC photon SPDC process basically happens in I mean, the photons will be generated in multispectral range. That means the spectrum of the photon will be different, because you can just have the pair. And since according to the energy conservation, the pump photon energy has to be equal to the energy of the generated photon. So the generated photon can readjust their energies to satisfy this condition. That means the photons can be generated anywhere in that spectrum. So and at the same time, the photons can be also generated in different modes, special modes. So for detection, that means we have to really be careful about the pair or partner photons. Let's say if you are just collecting a photon, you have to be sure about its partner to collect to get collected in the other side. Otherwise, if you're just seeing somebody else, then there will be no correlation, and that correlation, loss of correlation, is a loss of entanglement. So we cannot. So that is why we use a narrowband filter to extract the generated photons into a small spectral range, and at the same time, for special mode filtering, we use single mode fiber. So even though that for the experimentalist, multimode fiber is a very interesting fiber where you can collect more number of photons, and then very easy, very simple to do that one. But multimode fiber gives this poor visibility, because you are having a noisy photons that you are not, the photons not intended for this purpose is still being collected by this multimode, because it's allowing everyone. But single mode fiber, on the other hand, basically collects the Gaussian mode. So we are just collecting the photons generated in the Gaussian mode or fundamental mode. So always we are sure about the modes we are collecting. That is how this the single mode collection, even though it reduces the overall numbers, but it improves the quality of the photons or the quality of the state. Then we do the state fidelity, just a simple using this data, we can just have that, and then the state fidelity is something around 98%, means almost close to 1. And since we are just dealing this system in a Sagnac loop, and Sagnac interferometer is a stable interferometer, that's why we just see a very stable single photon or entangled photon that is coming, which is recorded over 6 minutes, something. We can just have that one, so you have a very good stable photon. So that is what we see. Now the question comes, basically, since you have efficient one, can you just improve the pump power, and then you get more number of photons? Or means how much I can improve the brightness? Means, is there any upper limit? For that, we keeping all the parameters fixed, we try to increase the pump power, which is easily available for us. So we can just improve the pump power and then see the interference visibility. And as expected, when you are just increasing the pump power, then the interference visibility or the visibility to measure the state basically is just reducing like this. And at some point of time, when you are just having 5 milliwatt of pump power, basically this visibility is coming around 71%. After that, it's no more a quantum source, because Bell state will be less than 2. So that this study basically shows us, even you have everything right, but you cannot really just increase the brightness to astronomical range. There is certain upper limit. You cannot really just go beyond that. So and then if you just keep on pushing it up, it comes with the cost of something else. That's why I always believe that one, no, you cannot really just get that highest visibility or highest fidelity of the state with very high number. It's impossible, because these two are simply orthogonal. So if you're just trying to improve the brightness, then you have to compromise with the state fidelity or entanglement quality. But you cannot really just both of them getting the right. It's impossible. So this study, so then basically, in all these cases, we try to use the source for a very low power. So let's say if you have just 1 milliwatt of pump power, that will be enough to generate large number of photons, and that can be used for this communication. That is what we have just when we are just demonstrating it for this QIQT. That is the source we have just used, which is still giving a good number of counts and key rates. So then I have just reviewed some the state of the art. What are the what people have just reported, and then you can see this our source basically gives the highest brightness till date, because we are basically using the optimum parameters one can explore to get these kind of sources. So that is why you cannot really just beyond this number you cannot really just go. That is what I believe. And you can always improve the detection system to increase the numbers, but when we define the spectral brightness in this form, the number always is somewhere there. So you cannot really just improve it to certain level. So you cannot push that beyond this level. So that's why still it stays as the highest brightness that source can produce among all the source used so far. And then there is a comparison when you are just using a single mode fiber where you have a high state fidelity, then you pay the price with the low number of brightness or spectral brightness. But when you are just trying to improve the brightness using the multi-mode fiber, then the state fidelity is going to really major, because perhaps it's going beyond that one, because this you can see the visibility is coming close to the limit. So that is what I said. As I said, just to justify the statement I just made, it's something like this. And if you're just trying to improve the state fidelity, then you have to reduce this brightness, or if you want to increase the brightness of the source or large number of photons, then you have to reduce. You have to be happy with the fidelity of the source. So now, so far it's looked good, excellent, and then you can just have a good source, sufficient number of photons, detected photons that can be used, and in fact we use it. But when we are just going for the payload kind of thing, then when we are just talking with the designers, they say you have too much constraints to the systems. What is that constraint? So just to give an example, let's say if we just fix this measurement, we are now just trying to study the SPDC ring or the down-converted photons, how they are just distributed over this ring. You are just trying to collect that one. So for example, let's say we have this palm wavelength is fixed, and then we fix the crystal temperature 25 degree, and we are just detecting this one. It's perfect. And then we optimize the system. It's giving perfect parameters what we are looking for. Now, if you change the crystal temperature by some means, something happen, and then crystal temperature change, like 27 degree, then you can see the SPDC ring goes down. And then your detection system, which is static, fixed, you will miss everything. At the same time, if the temperature goes below the set temperature, then again, you do the same thing. So that means my fixed detection system will miss the photons. My crystal temperature problem, the designer said, okay, you have this problem. And then we try to understand how much is the variation, where it is. So let's say if you just fix this and then try to change the crystal temperature, and you can see the coincidence counts is coming in this shape and falling. And then if we make just some estimate, like the coincidence count variation of 10% coming due to the crystal temperature variation of plus minus 0.12 degrees centigrade. So that means the crystal temperature, what typically people use for all periodical pole crystal experiments with the periodical pole crystal is 0.1 degree centigrade. That is what we have to maintain, even we are just if we are using this kind of system for any or any problem. So you can just have that temperature stability, and then you have the stability. What I was just showing previously, it stays static. Everything is good. But the problem is when you are just sending into the space, or the payload we are making, the entangled photon source, you are sending into the space where the environment or background behaves very erratically. So you cannot really just tolerate that one. That means there stabilizing the system or stabilizing the source by this margin is very challenging for the designers, and it's just a very resourceful also. So you need a huge resources to stabilize that. And once you are just trying to compromise that and improve your resources, or you are exploring your resources more, then your everything goes up, and cost, mass, power, budget, everything. There is one problem. Second problem is, let's say, if you fix the temperature and then see the, because when you are just sending the payload to the space where you have to have a diode laser. In case of lab, we are basically using a diode laser or a sophisticated laser whose wavelength is stabilized. But when you are you cannot send those bulky systems to space, so we have to use a diode laser, which will be low in mass and power consumption is less. But this diode laser is having the tendency of mode hopping or mode jittering. That is a natural process for this one, even though you have stabilized it, but still it will be there. So in that case, we try to see if there is a change in the wavelength of the laser diode, which you cannot really control, then what will be the change in the SPDC photon. So you can see here, it's a Gaussian distribution, it's going to the annular ring anywhere. So by change of 300 gigahertz frequency, by just simple frequency shift by 300 gigahertz, will make my system completely, my system missing all the photons. So you cannot really just see this. Okay. Now the question is how to solve this problem where we don't, we can just minimize the resources required resources. For that, we have basically, if we want to just minimize the resources, then we have to just translate the SPDC photons or SPDC ring into a perfect ring whose size is independent to the variation. So that means if I can just, because my detection system is fixed, if we can just arrest this SPDC ring size constant over the change in the crystal temperature or wavelength, then that will be the fantastic proposal. One can really just think. So basically here we are just showing this, you can see for different crystal temperature, even though we have that variation in that here, the variation is happening, but here you can see this ring size remains unchanged. And then you can just have this kind of wavelength variation. I have just compared that we can just do. So how we can do, that is what we have just done in the lab. Basically what we did, we keep that entire experimental setup fixed, then you use a lens to focus this ring at that at the detector plane, and then we have use an axicon, basically just doing the Fourier transformation. So the this axicon will act as a Bessel beam. Axicon will transform this beam, input beam, into a Bessel beam, and that Bessel beam is Fourier transformed into by this lens into a perfect ring. That is what we just see in case of structure beam experiments, where we generate perfect vortex, where the vortex size goes up, but still the perfect vortex size remains unchanged. That is what we are, that similar technique we're just trying to implement here, where any variation in this one will not change the position or the size of the SPDC photon. So, but by simply just adding two passive optical components, which is readily available in the lab. So then we get this kind of thing, and then we measure the same coincidence counts curve, where you can see this is the initial measurement, where you can just have that this variation. Whereas we can use in this kind of technique, you can just see is a broader temperature range. And if you're just using a multimode fiber, then you can see even in a better temperature stability or relaxed constraint. And in fact, we just take the comparison, then we can see for the same 10% fluctuation, what we see in case of the first experiment, where you see the temperature stability requirement is plus minus 0.12 degree. Here we need 1 degree. That means you can just easily do that one. You have a Fourier maximum of 2 degree, then it's easy to do that. And a similar kind of thing here in case of wavelength, we see that one is a 300 gigahertz kind of wavelength shift can also give you the similar kind of counts variation without any problem. So then we just measure this coincidence counts. It's it's entanglement parameters, whatever you had just done previously. So then this is a good parameters to take with the state fidelity 95%. And then the one of the problem that we are just trying to address at this moment is this coupling efficiency, what we got 18% in the previous case. Here we are just getting into 5% or 7%, something like that. So that efficiency we can just improve by using different collection system that we are just working on. Perhaps we can just improve the overall count. So, but still not to complain, basically the counts rate or spectral brightness in this case coming around 20,000 counts per milliwatt, something like that. So that is good enough for any field experiments. So as I said, we have this SPT seeding and then this Quantis payload. That is the payload we are just planning to send to space for doing onboard experiments just to study the entanglement property of the source and its HOM interferometry. That will be the first experiment in space doing that HOM interferometry. Now, since we had just 2 experiments, 2 different experiments, and for these 2 experiments, you need 2 different sources, but we made the same source usable by the 2 experiments simultaneously. But how we did? Basically, we have this SPT seeding. Now we here you can see these photons are always falling diametrically opposite. So if a photon is here, then its partner will be always here. If the photon is collected from here, their partner will be there. So there will be no crosstalk by that. So that means we can just collect a photon from here, forming an entangled photon source. We can collect from diametrically to opposite point in orthogonal direction. We can form another entangled photon source, and vice and many more. So by cutting it in many pieces, we can have many number of entangled photon source. They are independent. So because the property of one is not dependent on other. So in this experiment or the payload, what we are just doing, we are just dividing this SPT seeding into 2 sections by using D-shaped mirror, and the gap between this D-shaped mirror is allowing some part of this beam, what we said, passing through this one, and which is being used for HOM interferometry experiment, and other sections diametrically to opposite point. These 2 points are going for the entanglement studies. That is the geometry, optical layout, and the mechanical structure layout, which has transformed. So we take this in the static interferometer. That is what I explained already. And then dichroic mirror, and then it's divided into 2 sections, and where we are just having 2 experiments, and then there is another experiment. Total will be doing 3 experiments on board simultaneously. So and then in the lab we have studies those sources and studying this HOM interferometry, how that is coming. That is basically it's a good HOM visibility, and also. And then entanglement quality is also something like that one. We can just get that coincidence counts something around 40,000 per second. And this is basically the payload, what I was just explaining. This is the mechanical structure, how it looked like. Basically using the same optical design, it's being implemented, where the source part is here, which is defined, which is shown by this diagram. This input laser comes here, and then this is a dichroic mirror, and then this is the lens forming this, and then we have this analog interferometer forming here, and this reflected photons from this dichroic mirror will be divided into 2 sections. One section pass through this with the doped prism, and then splitted by the right angle prism or prism mirror to these 2 ports for this HOM interferometry, and that the reflected part here coming to this point, where and the other point is here. So these 2 will be used for entanglement study simultaneously when we are just studying this HOM interferometry. In fact, some other plans are there that will come in time. Okay, so that is what HOM interferometry actually measurements in the lab when we just because the lab model of the source we have tested in the lab using definitely the sophisticated laser, but we are yet to implement using this diode laser in due course of time to see a good HOM visibility. With basically here is a 10 nanometer bandwidth filter is used. 3 nanometer bandwidth filter is used, which is giving the full width hub maximum of this HOM curve to be around 260 micrometer. and some of the parameters in terms of the coincidence and so on. Okay, so in conclusion, so I think I have just made it in time. Basically, these are I hope I have convinced you that one can use the type 0 phase matching technique in periodical pole crystal to generate a bright and develop bright entangled photon source, and then the constant of this source can be further relaxed by using a new geometry. That means basically translating the SPDC ring into a perfect ring, and then this approach basically reduces the requirement of the resources for field deployment. And we have devised multiple entangled photon source from a single. So even though I have just shown you 2, but in the lab we are just making it 4 sections or so, and that can be used. Let's say you have from single resources like nonlinear crystal and laser diode. If you can just make 4 source independent sources that can be used, that can be multiplexed to make a QKD or quantum key distribution over multi-parties. Like you can just, you have a plan to implement it for 3 parties simultaneously. They can, so far people actually do this between the 2 parties, but we're just trying to make it in the 3 parties. But in that case also resources are huge, or optics will be huge. But let's see, we can just get something interesting on that. And using this indigenously developed entangled source, we have developed a payload. That is basically the structure model is being developed or fabricated, but it's a optical means it's a lab model have been tested in lab, and that perhaps go at some point of time in future. With this, I thank you all for your kind attention, and then I'll be happy to answer the questions you are having.
Yeah, thanks, Goutam, for this wonderful talk. Really, I too heard, really interested. It was very, very interesting. So, questions. I have one question in the chat.
Yeah.
Which is saying that what are the disadvantages from Aniket? So, what are the disadvantages you notice by using type 0 phase matching?
Actually, initially why these periodical pole crystals are there a long time. I mean, it's not like that. We see in literature people normally use periodical pole KTP crystal in type 2 phase matching because once you have generated the photons, you have to separate them. The partner photon has to separate. So they use type 2. Previously, people used to use the geometry of separating the photons using generated in orthogonal mode in type 2, because if the photons are orthogonal in polarization, you can just put simply a polarizing beam splitter and separate them out. But in case of type 0, as I said, in case of type 0, the photons have the same polarization state. So that means if the photons are overlapping or collinear and they are co-polarized and co-wavelength or same wavelength, degenerate wavelength, where you get the maximum conversion efficiency or maximum gain, then you cannot really just do much because you cannot separate. But again, sometimes people use non-degenerate in case of type 2, or type 0 also you can just use non-degenerate, where your wavelengths will be different. But when you have a different wavelength, then they will acquire different phase in the nonlinear crystal. So there will be, that is why you have to just compensate the phase also by using other optical components. But in type 0, if you can just translate that collinear to non-collinear, then you can just specially separate the photons, even though they are carrying the same properties in all degree of freedom. So that is the beauty of this kind of scheme. And since both of them are having same polarization state, same wavelength, there will be no relative phase. So you don't need to really just compensate anything. So you don't need to use additional optical component to compensate it, whereas you get the highest conversion efficiency. That is what I think, just disadvantage was something, how to separate. And then once you find that, you can just specially separate them, then it's no more disadvantageous, it's advantageous, people can use that.
Great. So the next question is from Amber Hastinapuri. What are the limitations of using waveguides for SPDC? Can we totally get rid of the problem especially.
Yeah, waveguide, basically you can just have this waveguide, but coupling the waveguide and then collecting the photon, this is also, it's having its own challenge. And especially when you are just bulk crystals are used, when you are just dealing with orbital angular momentum or structure beam, where you cannot really couple the structure photon in that case. So apart from that one, generation rate waveguide will be compact and that one can do, but you cannot really just use this kind of geometry where you can go to the non-collinear geometry. So that is always a collinear, and then you have to have that wavelengths separated, non-degenerate, not degenerate, non-degenerate, just wavelengths are separated by their wavelength, or you have to use type 2 to go for that polarization state for the separation. So apart from that, these are the two issues for the waveguide, where and then when you are just trying for higher dimensional entanglement, where using structure pump beam or orbital angular momentum, that case you cannot really just use waveguide. So waveguide has, both the fields parallel, they have their own advantages and disadvantages. So where I will not be really selling this one like a bulk crystal with the base, because it's a bulk crystal is having its own limitation in the form of, just system it's not very compact. So you require a lot of footprint or big footprint to accommodate. Whereas waveguides, if you're just using the footprint, it goes down, but depending upon the application, you can always choose which one to use.
Yeah, great. I had one curiosity. So you mentioned about this diode lasers with this longitudinal mode of beam. So typically, you said sort of short thing is 300 gigahertz. So that's a huge mode hop. So I was just wondering, these days, these optical lasers, etc., temperature controlled and non-ECDLs, is external cavity diode lasers. So
yes.
First question is, would they have similar? They don't have that much of mode, right?
Actually, this experiment we have used 3 different diode lasers. Means two different diode lasers. One is a optical laser that is giving you the very stable, because it's a optical laser itself is a
very stable,
very stable, but it's very bulky. You cannot really just accommodate inside. So we are just trying.
Sorry, I missed that. What did you say?
So you cannot. It's just a bulky system.
Bulky
system. So whereas when you're just going for the payload, where you need a very small one. So that's why we just found some on-dex laser diode, which is having it's a TO-CAN kind of diode.
Just a package, actually.
Just a package. So in that case, it's relatively stable, but it's sometimes just more hops.
So I was just wondering, one of these easy things is to just lock it to a rubidium cell, and then it gets.
Yeah, you can. In principle, you can just do
that. But again, that is.
But then again, it just adds up to this one. So in fact, Singapore has sent this diode. What we are just I'm talking about. So they check the health of the laser and then see if the situation is favorable. Then only they will operate. Otherwise, they will not. Okay.
So these are tunable lasers, or these are not tunable?
No, it's just a fixed one, but sometimes.
Oh, then you cannot use but then you cannot use this rubidium cell thing.
No, yeah, it's just you have.
Tunable, does it lays over a big frequency range?
No,
or
it's only a 405, because we try to get.
But there is no because 405. Oh,
405. So rubidium we cannot use. So they have used volume Bragg rating, where it stabilizes the thing, but still we see sometimes mode jumps are there, and then you are just missing everything. So then we try to address that one.
I see. Okay, great. So there is a huge question. Thank you for the talk, Subhashish Barik. I was wondering about the beam alignment and mode matching through lenses challenges in your experiment. As I saw in the schematic of the setup, single mirrors guiding up 2 to 3 beams. So essentially, how much of the space this setup takes?
Okay, that's a good question. Good question. It means he's asking from the actual practical limitations. What I don't face. Our group member or student, those who are aligning data.
Those who are actually doing stuff in the lab. So, our time for these things is over.
Yeah. So simple answer will be you do it, and then they will do it. But I'll not go to that one. Basically, what I said.
So this mode matching thing, maybe you can comment on both of this.
We all are.
Absolutely.
We all were in a PhD student. Means we spent as a PhD student, and we faced the pain always.
So this mode matching is an issue, do you think? I mean, we have multiple.
No, that is not a problem. So basically, just what is the size? I'll answer. So because aligning Sandbag interferometer is not a big deal.
Nice.
And in this case, actually, we are dealing with a single photon, which is collected by a mode field diameter of 5 micron. That is a challenge. So you have to really,
it's very small.
It's a precisely you have to align. But my group members, you can just make a half day, they can make it. And the system what we have build, what I am just saying as a prototype that can be used by anyone. I mean, let's make it, and then I can just perhaps just give it a loan to others whosoever interested to use it. Is basically coming around 20 centimeter by 20 centimeter footprint of the source. So basically, you will have a fiber output that will carry the single photon or a entangled photon that can be used for any application. So it's a 20 centimeter by 20 centimeter, including electronics package.
It's only 5, like 6 in what? Yeah, 8 inch.
Yeah, something
8 inch by 8 inch.
So,
8 inch by 8, not even 1 foot.
Yeah,
8
not
inch
even
by 8 inch.
So, and we can use further optimization to even squeeze the size into a.
But that probably depends upon the payload requirement, right?
Yes,
so I think 8 inch by 8 inch is very small anyway.
Yeah.
Extremely small.
Yeah. So this one I am just we are also because the source we are just building, it's just, there is mostly no tunable components. So everything is static. That is how we are just building the prototype, where you will not have any knob to adjust or control. So basically, that is what we are. So then your the system stability will be even further means enhanced. So we are just trying to make it robust, so that even you throw, then that can withstand the impact. So
yeah. So this is the last question. Let us take a last question from Aniket again. So he says that when you're increasing the temperature or changing the wavelength and using the axion to compensate the ring size, you mentioned temperature change of one is permissible. What happens if temperature is increased more? The ring size remains same, but what is the problem?
So
yeah, so basically saying the ring size is changing, but then if it goes more than 1 degree, then what happens?
Yeah, so okay, let me.
So he says that changing the wavelength using this thing, you mentioned the temperature change is 1 degree is permissible. So what happens when you have higher temperature change? What is the issue that arises?
Okay, so it's a okay. Let me go to that presentation. So what we are just trying to say, you can see here, it doesn't matter where you are. It's matter that when I fix everything, after that there is a variation, whether I will be getting it or not. That is what I am just trying to say. Let's say you can operate anywhere. The source will give you the same brightness, but perhaps counts will go down because your area means photon distribution or photon density will go down since the size is increasing. Let's say if you fix anywhere, any one of that temperature, that doesn't really matter. So then
the stability is important. I think what you're saying, Goutam, is that after
I'm just saying that after everything is fine, if there is any change, do I have to really worry about it, or I have to do that alignment? So that is what we are just saying. Let's say even the temperature of the crystal changed by 1 degree, the system will be stable with that.
So
if it is going beyond that, then we have to again realign.
So realign because of what actually? Because of the beam path is sort of getting.
Yeah, so ring size is going up, so you have a detection system fixed.
So,
and then the ring is not falling on it.
You have to basically, there's an asymmetry in the thing.
Yeah.
Okay, so I think I'm sure the participants can access Goutam easily.
Yeah.
You can drop an
I'll
email.
Be happy if there is any.
Very happy. Sure, I mean, that is all. That is how we are all disposed. So again, thanks to Goutam for great talk.
Goutam and Oyan, both of you, thanks.
Okay, thank you, sir.
Thank you. Yeah.
Thank you. And see you sometime.
Yeah, we are going to have a conference soon. I'll call you, not this physically.
Okay, sure.
Bye.
Okay, bye.
So see you all tomorrow. Goodbye.